In this video we will talk about low frequency sound propagation through different wall configurations in double leaf walls. And it is Stefan, Sofia and Siegfried who has made this video. So what is a double leaf wall? A double leaf wall is a wall with two layers. For example, two gypsum boards connected with studs. Here in Sweden, this is a very common type of wall. To study what effect different wall configurations have on the amount of transmitted sound, 6 different wall configurations are made. The first one is a base configuration for a simple inner wall with single gypsum boards surrounding 70 mm studs placed 450 mm apart. In the second configuration, a second gypsum board is added to the receiving side of the wall. For our third configuration, both sides of the wall have double gypsum boards. The fourth configuration has only single boards, but the distance between the studs are increased to 600 mm. For the fifth configuration, the wall is made thicker by increasing the stud width from 70 to 145 mm. In the final configuration, everything is as in the first one, except that no air is added to the cavities in the calculations. The wall is 2.5 meters high and 3.6 meters wide. To simulate the transmitted sound, the finite element program Abacus is used. After the wall configurations are modeled in the program, 2 analyses are made. The first one is a model analysis that finds the eigenfrequencies for the wall. That is the frequencies where the wall is vibrating with standing waves. The first 5 modes are shown now. In our model they show up between 20 and 70 Hz. The lowest ones are seen in the wall with stud distances of 600 mm, and the highest ones are found in the thicker wall. The base wall and the one without any air has exactly the same frequencies. The second analysis made was a frequency sweep. And that is a point load that vibrates the wall in different frequencies. From the frequency sweep, the acceleration on the opposite side of the wall from the load was obtained. This data was then processed in MATLAB by creating average acceleration values for each frequency. Here are all the model shapes once more. The 3 on the top are the first ones, and they are the same in all 6 models. But interestingly enough, the ones below to the left are only valid for the walls with the same thickness. The ones to the right show up in the thick wall in Model 5. It makes sense because the wider studs make that wall a lot stiffer in the vertical direction relative to the horizontal direction, compared to what is seen in the thin walls, which makes the model shapes appear in a different order. This picture shows a plot of the acceleration values plotted against the frequency between 15 and 85 Hz for all the models. The peaks that can be seen are where the eigenfrequencies are. When the frequency of the load that is applied corresponds to the eigenfrequency of the wall, it results in a large transmission. The reason that peak number 1 and 3 are so much bigger than the other peaks is because these eigenfrequencies have antinodes in the center of the gypsum board. This is also where the load is applied, which creates a much larger effect. Here the base model and the model with 2 gypsum boards on one side of the wall have been plotted. It is clear that the gypsum board contributes with a stiffness to the wall, which reduces the transmission through the wall. Here the base model is compared with the one with 2 gypsum boards on both sides of the wall. Having 2 gypsum boards makes the wall even stiffer and reduces the transmission even more. Here it is compared to the one with greater distance between the studs. Increasing the distance between the studs reduces the stiffness of the wall, lowering the eigenfrequencies. The transmission of the wall was not affected noticeably. This is the base wall compared to the model with a thicker wall. The stiffness of the wall is increased significantly, greatly increasing the values of the eigenfrequencies. Once past the first eigenfrequency, the transmission is not affected. This is due to the fact that double leaf walls behave as 2 single leaf walls after the first eigenfrequency. So both the base model and the thicker wall behaves the same way. Here the base model and the model with no air have been plotted. No significant difference exists between the two models. Research on the effect of air in the wall model says that it only plays a part after 90 Hz.